This conference will now be recorded.
Jumping to the last one, recycle. Here what we call recycling is really what I would say more of reusing, because what that is mechanical recycling, and let's separate the metals and glass, which actually can be recycled in kind of a holistic way. Let's say you can make another beer can from a beer can, and you can do that almost indefinitely. With plastics and with fiber, that's not the case. Every time it goes through the system, it gets degraded. So really, we get so many reuses out of it, which is fine. It's good to have efficient use of the materials, but ultimately, the recycling system is just delaying the inevitable trip to the landfill or litter or wherever it's going to end up. So that's recycling as we're doing it today is not going to be a solution. We're just not going to get there from here. Then looking at reuse, right? So that often seems like we're seeing some things today with Loop and TerraCycle where folks are looking to reuse containers and things like that. Now, reuse as right after reduce totally violates that notion, right? So if we're building something to reuse for reusability, we have to make it really stout, which means that we need a lot of material in there. So we're totally going against the reduce side. Now, the equation is an economic one. How much stuff do we have to put in there and make it strong enough to get so many trips to make reusing it economically viable? But on top of that, if you're reusing containers, you have the impacts, the costs and impacts, environmental impacts of the reverse logistics, water use, chemical use, and all of that. So reuse almost never makes sense from an economic or a sustainability standpoint. So by and large, reduce, reuse, recycle, there's some nice things to do in there and they make sense to do, but when we're talking about trying to solve the problems we're looking at, it's just not going to get us there. We have to do something different. So that kind of reinforces that second bullet. Mechanical recycling is linear, right? So ultimately, if we make a water bottle, from the water bottle, we might be able to get some more uses in a water bottle. We have some grades of PET and things like that where we could actually do that, but still the quality of the polymer is being degraded each cycle. So ultimately it's going to end up either in a landfill or maybe as a sneaker and then in a landfill, or maybe as a sneaker, then a park bench and then in the landfill. So ultimately it's really a linear path. All right, it's not a circular one. All right, another one, bio-based plastics. And I have to be very careful here because my department is agricultural and biological engineering, and we love making things out of things that come from biology. And that's fine. And there's some important reasons to do it, but we can't lose sight of the fact that growing stuff is impactful too, right? It's energy intensive, requires water and fertilizer and all of the stuff that goes into making it. So those have impacts. But at the end of the day, when it comes to packaging, like my world, and the plastics that come from bio-based materials, is that when we're done with them, they're still plastic, right? And we still have to somehow get rid of it in a responsible way. So just making it out of a bio-based source is not really a solution to the problem. All right, that leads us to the next bullet, where biodegradability, right? So the composting idea, or biodegradability. This is one of the most, what I would say, this is my opinion here, but this is one of the worst ideas that we could come up with, frankly. And here's the reason, all right? So if you consider a football field, I should have had a graphic for this, but a football field, right? 100 yards with area, right? And it's covered in waste, right? Waste plastic. And you consider that's the amount of material we're producing out there in the world. Now, we are very sensitive to the litter in the environment, the ocean litter and in the woods and all of that kind of thing. And if you consider the amount that leaks out of the system, it might get us to the 1 yard line, right? So that amount is going to end up in the environment, and it's unfortunate, and that's something we have to solve. But most of the other stuff is going to end up in a landfill. Now, landfills, sanitary landfills are meant to entomb what we put in there. They're not meant to be bioreactors. If we want bioreactors, we make some very good ones here in our department. But landfills are not supposed to act as bioreactors, but they do, right? Water leaks into them and we have anaerobic degradation in there, and that releases methane. The EPA says that landfills are the third greatest contributor of environmental methane out there. So if we start producing all of this stuff out of biodegradable materials, very few opportunities, there are very few municipal opportunities to compost it or convert it. So most of that stuff, right, the 99 yards of it, is going to end up in the landfills producing methane. So we're kind of not really solving a problem there. So in that regard, we'd be better with plastic that's not biodegradable, because at least we would be, it's a carbon sequestration issue, right? We would basically take the carbon out of the ground from fossil fuel, turn it into plastic, and bury it again, and it's gone for good, right? So that's actually an interesting thing to think about. All right, moving on to material-specific technologies. Here we have different companies producing all kinds of great products. Let's say a juice box, right, or a Capri Sun drink, very convenient, great for the kids, things that make our lives very much better. But when you look at those materials, like the juice box, there are multiple materials in there that, when put together, they're not recyclable.
Yeah.
And so I hear somebody talking, so I'm just sorry. So in either case, when we talk to some of these companies right now, they're so focused on solving their problem, right? So Tetra Pak is working with a German company to develop technology that would make juice boxes recyclable. The problem with that is that my municipality is most likely not going to have that technology, and they're not going to go through the trouble of separating juice boxes to put into that particular process. So in the end of the day, it's those specific technologies don't lead us to solutions. All right, the next bullet, the multi-layer plastics, metallized materials, all kinds of things like this, they add great value, right? Our soldiers rely on meals ready to eat. We're not going to be changing that. We've gone from, in the reduce side of the reduce, reuse, recycle, from glass jars, plastic jars, into flexible. Right now, you could buy sour cream in a squeezable pack, right? That squeezable pack has multiple layers in it, and by virtue of it coming together, makes it very difficult to recycle. But it's very minimal, and we have environmental gains from that multi-layer material there. So that's something that's not going away. In fact, the trend is much more of that than the opposite. And then finally here, hopefully, I think, before COVID-19, there was this cultural momentum against plastics about, banning straws and banning cups and banning all kinds of plastics. I think we have discovered that, that single-use plastics and the resiliency of the supply chain that provides them, right, for the PPE and everything else, that needs to be there, right? So we all want, when you go into a hotel and you grab a cup, you're going to want a wrap around it so that that it's clean. So these things are here to stay, and I think we need to kind of accept that and move to solving the problem. So we're not here to fight about that. I think the thing to do is if plastics are good, plastics are not good. The idea here is that we're going to be living with plastics. We need to figure out how to solve the problem. Next slide. Okay, we have a problem, right? I just went into Bing and ocean plastic, and you get these kinds of images. Some of them are doctored, of course, some of them not. And we are all very sensitive to plastic in the environment. Plastic gets a particularly bad rap, I think, because it floats, whereas a beer can and bottle, they sink. So we see it, and of course, just by the fact that it floats, it also can interact in nature, and nobody likes to see that. So, I'm not trying to justify any of this. I'm saying that we have to figure out how to solve it. But the problem itself is not plastic. We can't solve this problem by eliminating plastic, because we're not going to do that. That's a crazy notion. And what I would say is that the plastic is not the problem. It is the way we're handling waste. And for that, we have to help municipalities make the right decisions for us, because ultimately they do have the responsibility for handling waste. That's not something we can put onto the producers. Next slide. Okay, I kind of went through this. So reduce, reuse, recycle, ultimately these things are linear. So I'm just going to go through that. So maybe just next slide. Okay. Here is just to kind of reinforce the notion. A colleague of mine up in Toronto, and Canada, Toronto, very forward-leaning in sustainability. They've been trying to do a lot of these things. So we could almost look towards places like Toronto as a cauldron of experimentation for a lot of bad ideas that they've already tried. So Calvin studies this and does a lot of great reporting on it. But here was a quote that I particularly appreciated. And he says, when evaluated, and this was done for Glad products, so bags, light plastic bags. When evaluated over the entire life cycle of a product, package lightweighting will often result in superior environmental and economic outcomes, even in instances where those materials cannot be readily recycled and are subsequently landfilled. This is particularly true of lightweight packaging used for food storage. And it's interesting that he brought up the food storage there, because what is the greatest sin is that when packaging fails and we lose the food, because there's a lot of environmental footprint that goes into the food. So a lot more certainly than the packaging. So it is the greatest sin to lose the food when, if we are going to chintz, I should say, or misdesign the packaging in order to, for some benefit, and then we end up losing food. Next slide. Next slide. Okay. So sorting, right now here we're driving everybody crazy. So I have consumer sorting and then the MRF sorting, material recovery facilities. And basically I think there's a disconnect. What I see is a disconnect, right? When we talk to industry about recycling and sorting waste, and we talk to the folks, the good people in the great state of Florida about recycling, they're thinking about it differently, right? The folks think that when we sort all this stuff, we make stuff from it, right? And that's totally not true. What's happening here, maybe go to the next slide. All right, so this is different forms of sorting. We have the consumer, we have the MRF doing manual sorting, and here we have highly automated sorting. All right, and then go to next slide. So what we're really doing, if you talk to the industry folks, is there are certain materials in there that they want, right? So they want the clear, clean, no color, right? When I say clear, so there's no color in it. So they want the clear, clean material, so bottles, and of those, usually just PET and high density polyethylene. That's all they really want, right? And it's all they really make any money on. So as we improve our sorting, what we're really doing is we are purifying those very narrow streams of materials, right? There's plenty of PET in the sour cream pack that I mentioned, the squeezable thing. There's PET and all kinds of other stuff, but it's very difficult to get at. So the easy stuff that's clear and clean they want. And what we're really doing by improving sorting is actually creating more waste that ends up in a landfill. So even though folks like, possibly my mother, who likes to recycle everything or thinks that somebody's going to figure it out, she'll put it in the bin and she'll say, well, somebody should figure out how to deal with that, right? The reality is that most of that stuff just gets diverted right into a landfill. All right, so here we're just separating the wheat from the chaff. We're not really making good use of that stuff. So the dirty stuff, the things that have labels that are adhered on them, small things like a Keurig K-cup, multi-layered materials, that stuff is not getting recycled. Next slide. All right, on top of that, we have committed, right? We're sending these heavy trucks that get about 3 miles per gallon to pick up the what we call recyclables, which over time has diminished in its weight, right? So a beer bottle, for instance, or a beer can has lost a lot of its weight. So the economics of sending these duplicate trucks around to collect the recyclables is killing the economics of recycling. So on top of that, on top of the environmental impacts, it's a very challenging thing to do. All right, so next slide. Let's get into the solution here. All right, so as we're talking about, this is kind of a summary here that, what we think we're doing, right? Where we take all this, or this is actually what we are doing, right? So we're taking our municipal solid waste. We think we're sorting it perfectly. We think we have all these great technologies that are making use of it. And of the stuff that we actually do make, we're making things of less quality. And that's basically what it is. So next slide, what we should be doing is basically, is real circular economy, is looking to our waste as a material resource, and we have the technology to do that. And it's kind of like a tagline here, syngas, which I mentioned in the beginning. Syngas is the key to circular economy sustainability. We have the ability to create we have the technology that is robust and flexible. And what that means, it's kind of like an economic equation here. It's robust in the sense that it can accept everything that's in the municipal solid waste. It doesn't mean we would want to put everything in it, but it can take everything if we had to, right? So we can still, this doesn't mean we can't continue to do mechanical recycling to the markets that are economically sustainable, but everything else can go into this system. And from syngas, we can make plastics again. In fact, that's what the Chinese are doing. I'll show you that in a minute. So next slide, what this looks like. All right, so this is the technology that does this is kind of like an advanced version of an ancient technology of gasification. And I'm not sure you could see a mouse if I moved it, but anyway, I'll do it anyway because I'm talking about it. But in the center here, you have this vessel, and the top of that vessel is a traditional gasifier, a downdraft gasifier. There are different types of them in the world of chemical engineering. We've got fluidized beds, downdraft, updraft, all kinds of draft. But basically, the idea here is that we get the stuff hot enough that we break down the chemical bonds. And what comes out of it is the syngas. And over on the right-hand side at the top there, synthesis gas is a mixture primarily of carbon monoxide and hydrogen. And what you should see is carbon, hydrogen, and oxygen, which are the basic building blocks of everything that we pretty much make. All right, so the magic of this technology is that we've put it on top of what we call plasma-assisted gasification. And in that, what we've done is we've borrowed equipment that already exists in the metal industry, electric arc furnaces, plasma torches, things like that. And essentially what this is a lava machine. And in there is molten glass and metal. And ultimately, the material is shredded and goes in here. So anything, if we had an MRE, for instance, the metal foil that's incorporated in there would be melted down and recovered out the bottom. The rest of the stuff, the polymer coated, material there would be converted into syngas, which would be recovered. And what we're talking about here, now syngas can do a lot of things. We are advocating from a packaging standpoint, the circular economy approach, which would be to convert it into primary feedstock chemicals that we could then make new stuff from. So it would essentially be our oil well, would be our waste stream. And the stuff that we make from that is as good as new. Next slide. All right, so this is not new. Eastman Chemical has been gasifying coal for many years in Tennessee. They've actually converted a coal gasifier to run on MRF bundled waste plastic, right? So this is totally doable. They're doing it today. They're doing it to make syngas on purpose. And from the syngas, they make all kinds of great stuff. So Eastman is a forward-thinking company in this regard in the United States, but their technology is more of the traditional gasification. So it requires a high degree of sorting so that all they're putting in there is certain types of polymers because it doesn't run hot enough to be as robust as the plasma-assisted gasification. But at the end of the day, with the right feedstock, they can get syngas and they can be very circular. They call that carbon renewal technology. All right, and they provided this slide, and it's really their argument to try to convince people that gasification is not combustion. And so we'll accept that. We'll stipulate that gasification is not combustion. Next slide. All right, this is a graphic from the Global Syngas Technology Council. And basically it shows all the different ways we can use syngas. And what you see at the top there, I kind of modified it because I'm not exactly sure what was underneath it before, but it was, at the end of the day, we could use any carbon source to make syngas. The big bubble in the middle, syngas, can then go a bunch of different routes. If you go off to the left, we could just burn it directly and make power, which has been the folks who were interested in waste to syngas initially were all interested in that when oil was $120 a barrel and things like that. We're not necessarily advocating that because we don't see that as being circular, right? That's just taking fossil fuel, making plastic, and then making power from it. That's more like incineration. So we're not advocating that, but it can be done, right? For the hydrogen economy, there's a lot of interest in this for Toyota's building trucks and things that are going to be running on hydrogen. So there are folks that are looking to make syngas for that. On the right side in the red, this is what the German army did in World War II. They did not have access to petroleum, so they converted coal into syngas and then through Fischer-Tropsch chemistry made all of their liquid fuels that they needed, diesel, gasoline, and all of that. At the bottom here is what we're talking about. It is a chip shot step to go from syngas to methanol. We can't really transport syngas well because it's a hydrogen containing fuel, so you can't really liquefy it, but we can convert it readily into methanol. And methanol is a fungible primary feedstock chemical that's used to make just about anything. And in fact, in the last several decades, China has developed technology to convert methanol into plastics. And they now call that MTO, methanol to olefins. You can Google that. There's a big industry about that right now. In fact, it was probably the methanol to olefins technology that caused China to stop taking our recycled plastic. But in either case, we can also use that technology. And in fact, Honeywell is a big player in that right now, the MTO plants. Excuse me. And by and large, we would be making this methanol. Now, I want to say that methanol from waste will be, while chemically identical to methanol that you get from, from other sources, and most folks that are making methanol are using coal or natural gas or petroleum. But when we make it from waste, this methanol will be chemically identical, but it will carry with it the added value that society is placing on recycled content, right? So right now, the big brand owners, Procter & Gamble, Colgate, Nestle, Danone, all of them, Kraft, they're all making these pledges that by certain dates, they're going to have certain amounts of recycled content in their materials. But the reality, they're turning to their suppliers and saying, we've made the pledge, you need to supply it. And the suppliers are like, we don't know where to get it, because it's just not available. We don't collect and recycle enough material of sufficient quality to handle the demand. So we believe that methanol, recycled content methanol, will have a distinct market that will carry a premium. And what that will allow us to do is basically, like an Eastman Chemical could then mix 50-50 methanols, and the subsequent plastic item that comes out of it would contain 50% recycled content. And that's fine. So we'll get into that in a little bit, but next slide. So again, this is how is this created? So we're talking about in a robust way, taking virtually unsorted waste, or we don't have to sort it to the extent that we're trying to now. So we alleviate the sorting problem, which is a big problem. We make this syngas, we make methanol, and now methanol is it's not only a very flexible, versatile material, but it's also fungible, which I think is, this is kind of a deeper concept here, but basically Eastman Chemical says, we'll take as much methanol as you produce, right? They want it. They want offtake contracts for things like this. Now, the thing is, we might not need to even ship it to them, right? We can produce it, and then through an exchange, almost like a carbon credit type of a thing, they might take some traditional methanol, commodity methanol, off the market at their location, and then we would put ours back into that pool, and we would save the environmental impact of actually shipping that methanol from Florida to Tennessee. So I think there's tremendous opportunity for distributed manufacturing and jobs and great paying, great jobs that are in the sustainable type of environment. But from methanol, we make everything, and this is just to show that we make plastics, fuels, construction materials, paints. So the idea here is that there's an economic sustainability argument there, in that the methanol will serve so many markets that it's not like today when you have a Capri Sun bag and TerraCycle turns it sews it into a reusable shopping bag that you get 5 uses out of. This is something that can be used in so many different markets that are thirsting for sustainability, that there's some benefit to that, right? A clear benefit. Next slide. All right, so this is China's plastic production since 2010. Their first MTO facility came online in 2010, and every country of the world, every manufacturing country in the world is showing just absolute increases in plastic production. So the notion that we are going to somehow reduce or eliminate plastics is kind of crazy, and we have to stop thinking that way. We have to solve the problem. So in any case, the bullets here, coal and other fossil fuels are used to make syngas. That's how they're doing it in China mainly. The syngas is then converted into methanol, and the methanol can then be remade into plastics. And when we do that from waste, we can, we achieve a circular economy. Next slide. A little bit more of that. I just wanted to point out, Honeywell, I got to correct that slide, but again, just the technology here. And the graph there is kind of showing the operating conditions that result in greater methanol conversion. So in fact, one of the things that we're working on here at University of Florida is the technology to convert syngas into methanol. And there's a lot of great opportunities there, technological one. This is all about, catalysis and things like that. But there's a lot of process development that could go on in converting methanol or syngas into methanol. From there, the methanol to plastics to different, already established. Next slide. All right, then what comes out the bottom, right? So I mentioned, that the incidental glass and metal that's in there is also processed, right? So if we wouldn't necessarily want to be putting glass into it simply to melt it down and then to solidify it again, right? So there's other things we might want to do with the glass. To the extent that we have, easy to get at steel and aluminum, we would want to separate those out because those have already existing healthy recycling markets. But the rest of it, the foil in the MRE package, the closure on your Campbell's soup at hand that goes into the microwave oven that has the metal embedded on it and the number 7 plastic, that metal that would come off of that would basically be harvested out the bottom of this reactor. Essentially, we would end up with mixed metal ingots and a mineral oxide rock or other products that come of that. One company makes a glassy insulation product that has a high value. But at the end of the day, these are environmentally inert materials that can be used in construction. The rock would be used as aggregate in construction or abrasives. There's a number of applications that can be done with that. With the metals, another interesting thing that, in fact, is a national security issue is China's monopoly on rare earth minerals. And what we could actually do with this is be processing our electronics waste. And in that, this metal ingot that would come out would kind of be an ore for rare earth minerals that could then be processed for that. So from a national security supply chain type of a thing, we should be recovering that. Right now, we're just burying it in landfills. So another opportunity there. Next slide. This, again, from Global Syngas Technology Council. This is today's gasifiers globally, right? So we make syngas on purpose, all over the world because it's a useful, versatile chemical feedstock. And this kind of gives you a sense of it. You could go to their website and pull up the map as well and kind of dig in. You could actually click on each one and see what its feedstock is and all of that. But basically, you see that in Asia, the coal is a primary feedstock, whereas in Europe and North America, we use a lot of natural gas. We would like to see a lot more of our waste, being used to make syngas. Next slide. All right, so what's in our municipal solid waste? This is the wheel that comes from the EPA. And basically, if you work your way around there and add it up, what you'll find is that 85% about of that wheel is carbon-containing stuff that can be used to make syngas. And the rest of it, the metals and glass, they're not necessarily valuable to this process, but they don't hurt it, right? They get melted down and recovered. So that's that. Next slide. Okay, the next gold rush is recycled content. All of these big brand owners want it, they need it, and they don't know where they're going to get it. We think that methanol, the recycled content methanol, is going to be the market for that. So, and not only that, what I would say here is this is recycled content without compromise, right? So this is not a bottle that's been ground down, kind of beaten up 10 times and re-extruded, and it's kind of lousy material. This is every time you make it, it's chemically new. Right, so I talked about the fungibility of the methanol that would allow us to get additional benefits when we have kind of that's the nice thing about having a standardized output. And there might be some comments about, pyrolysis, right? So, what about pyrolysis? Pyrolysis is wonderful, but which is kind of like a cousin to gasification. The problem with pyrolysis, though, I would say, is that it is the process that is ideal for making char, like charcoal. That's what we historically use pyrolysis for. But pyrolysis makes two other things. It has a solid, liquid, and gaseous output. And when we use pyrolysis for recycling, the folks are after what they call pyrolysis oil, which is essentially the chemical stew, liquid stew that comes out. But that stew is kind of dependent on what you're putting in. So if we have pyrolysis instead of gasification, we're going to end up with lots of different stews, which make it much more difficult to exploit commercially because there's not one process that can just deal with the stew. So in this case, syngas, we know what it is, methanol, we know what it is, and everyone knows what to do with it. So there's a benefit in, kind of like everybody using Microsoft Word, we can communicate, right? So it's kind of the same thing, but on an industrial scale. Next slide. Okay, so this is about getting it all. The image here comes from a Florida company called Plasma Power, and they were Plasma Power. They were kind of interested in making electricity, which frankly is not necessarily a great economic equation, especially when fuel prices are low. But this image is on the inside of the vessel. This is what the lava machine essentially looks like. So this is a very hot, robust process, and by that it makes it robust. So we can handle where today we discard or we don't recycle dirty things, contaminated plastics. This is not a problem here. In fact, we use this process to degrade chemical weapons and things of that nature. So this could even be used for organic chemical hazardous waste, for the biological waste coming out of the hospitals. So it adds on to the municipal solid waste in our communities that we can process it locally and produce these good outputs. So, but the dirty stuff, mixed plastics of all types, the metallized stuff, not a problem. Laminates, foils, labels, adhesives, shrink labels, fitments, all of that stuff goes in, not a problem. Next slide. Okay, so what to do, right? What do I think we should do? Well, I think we should push to simplify our waste handling, right? Let's stop sending duplicate trucks down the streets and wasting all that fuel and carbon emissions and all of this. I think we would be, as a society, we would be better served by a campaign that made it socially unacceptable to not litter, right? Kind of like don't smoke, don't do drugs. If we just focus on not littering, I think we could have an impact on the amount of environmental litter out there. I think we should push brands to make a market for the recycled content, right? Instead of Walmart saying we want the recycled content, but we're not going to pay more for it. Instead, they should commit to paying more for it, and that way it would help to create the market for this material. Now, this is instead of, and we didn't talk about this, but what's happening today is that different regions are imposing what they call extended producer responsibility taxes and fees, right? EPR fees. And companies are jumping on the bandwagon saying, we're going to pay. So they're okay with paying a tax that sends money to money heaven, as opposed to, when they, and I think this has to do with who's making the decision at the company, right? So you have a chief sustainability officer that is making the decision at the top of the company saying, we're going to pay the tax because we're a good corporate citizen. And then you have the buyer who doesn't have the authority to say, we're going to pay more for the recycled content. I think that internally within these companies, they need to be, they need better communication to solve that. I think we should push suppliers to demand virgin quality materials as opposed to kind of degraded materials, right? So that will help to push people in this direction. Certainly support this initiative. So we have an initiative here at the University of Florida. We're creating an industry consortium for waste to syngas circularity. We've got a number of companies that have already joined it, about $600,000 pledged so far. And this needs to grow, right? And this will help us to get the message out to the municipalities and help them to make the right decisions, and maybe at the state and federal levels to have alignment of policies that will open up investment into these areas. A question that I'm most likely to get is, doesn't this use energy? Yes, it does. Certainly, there's almost going to be nothing that will compete with landfilling, right? Putting garbage on the ground doesn't take a lot of energy once you get it there. So this is always going to be that we're going to have to make a choice. What are we going to do? We either entomb our waste or we're going to do something with it. And whatever we do with it is going to require some energy. I would say that it's easier for us to promote renewable energy as a solution for that than to task all of our industries to invent new unobtainium materials that magically disappear when we need them to, right? It's a very difficult equation for that. So I would say that we could focus on the renewable energy side to power this and to deliver a circular economy. And then, of course, supporting distributed manufacturing from waste as a resource. And next slide. I think this is the last one. Oh no, one more. This is kind of like a summary of circular. I'm sorry, go back to that one, right? So paths to circular economy sustainability. So there's kind of two loops here, right? So the first one is if we were, it's kind of the bio-based thing, right? So if we make, there's a big initiative to make plastics from, sugar cane. There's a company in Brazil, Braskem. Braskem is making, they're making plastic from plants, which is wonderful. But still, it's polyethylene at the end of the day. So what do we do with it? But in either case, if we do have more bio-based materials, then that stuff is essentially biomass, and we can make fuel out of it, fuel and power, and that is circular and that's kosher. All right, so the more of that opens up that avenue for circular economy. But today, as most of our stuff, a lot of the stuff in the waste, I should say, is might come from a fossil fuel or something. Then the methanol and back to the syngas to methanol back to the material again offers us another route to circular economy. But both of these are powered through the syngas pathway. So syngas being the key to circular economy sustainability. And now the final slide. Okay, so basically promoting this consortium. We have a number of companies that are interested in this type of a thing. To the extent that we could get industry, academia, government involved, we have the opportunity to do that. So I thank you for your attention, and happy to take some questions.
Well, thank you, Dr. Welt, and we do have a couple of questions that are in the chat. I encourage you all to add additional ones in there. We'll go ahead and start with the first one that I see is, since it is a hot, robust process, does that mean that it is carbon expensive? Is the energy itself sustainable?
Okay, so it's an interesting question, and there's kind of like two ways to answer it. So the first part of this is that for the folks that pursued this technology to make energy, right? They, obviously they have to consume some energy. So the equation, when you kind of do the math, you typically will get, depending on the nature of how you produce the energy from the syngas, you would produce something on the order of 5 to 8 times the amount of power than the process was consuming. So that gives you a sense of how much chemical energy is carried through the process there. Now, we're not necessarily advocating that. We're saying that the cost of running that should come from a renewable energy source, and that kind of does make this kosher. So, you have to look at the total benefit and the total cost, and yes, the energy is a cost.
Gotcha. I think similarly, what is the power source? Natural gas, coal, solar, used to heat and produce
syngas. Okay,
yes.
So in traditional gasification, the feedstock is often used as the power source, right? So if you were gasifying coal, there would be some of the coal that would be essentially burned to make the heat, and of course these are exothermic reactions as well. So the process itself, the feedstock itself, is supplying the energy. Now, in plasma-assisted gasification, the distinction there is that the heat is totally generated electrically, right? So it's what we put in to make that electricity, which is why I'm saying that we should turn to a renewable energy source for this. And I think each facility could kind of figure that out on its own, to make it carbon neutral. So that's a way to answer it, but it is an important part of the equation.
Gotcha. And the second part of that is, how much water would be used to process, say, 100 pounds of waste?
Water. So water is kind of a cooling medium in this, and so it's not a lot. They're closed loop systems. This is not an intensive water use process. However, I would say this is that this gets into some chemistry here. So the thing is, when we produce this syngas, it often will come out in a ratio close to 1-to-1 carbon monoxide to hydrogen. To make methanol from that, we have to adjust the ratio to 2-to-1 hydrogen to carbon monoxide. So like what industry does, what Eastman does, there's a kind of a very classical reaction known as the water shift reaction. And what that does is we use steam to basically water to sacrifice some of the carbon monoxide. It gets converted into carbon dioxide and releases hydrogen. So it kind of shifts the ratio so that then you could do the subsequent reaction. So if we use that kind of reaction, it's a consumer of water in a stoichiometric amount. But what I would say from the waste standpoint, what we're looking to do right now, we're actually in a process of kind of getting a project together. We were looking to co-locate these facilities at landfills, which are emitting methane. So what we're looking to do is to harvest the methane, strip the hydrogen from the methane, and then use that for the stoichiometric adjustment. So I hope that answers the question, but this is not a big water user. And in fact, there's plenty of water in the waste itself.
Great. Next question is, how are carbon credits and the distribution of the methanol product handled? And would this mean that the methanol is released as the gasification facility?
I'm not sure I totally understand that, but what I would say is, I never was a believer in carbon credit and the carbon credit policy personally. So I kind of lost track of that. But I would say, I think what you're saying here is methanol a product of this facility? And that's an interesting question. And if that's the question, it's an interesting one because it has to do with maybe local jurisdiction and rules and things like that. So there are opportunities here, I would say, where let's say a municipality or one company would convert waste into syngas, and then the syngas would be piped to another company that would essentially buy the syngas and make methanol from it. Or that could be one company, I'm not sure. So not exactly sure how to answer that question.
Gotcha. And the next question goes along with what you were just saying before. And that is, can landfills be mined for syngas?
Absolutely. So here, definitely, right? So we could actually recover landfills and feed them through this system and use them as industrial parks. And that's part of this equation because part of the value there is to convert that land into a higher use and higher value. So definitely, yes.
There's a question, why should Walmart pay more for recycled content if it comes from syngas?
Why should Walmart be more for this? Okay.
Why should they pay more?
I'm sorry, I missed that. Say it again.
The question was, why should they pay more for recycled content if it comes from syngas?
Oh, I see what you're saying. Okay,
It's
so
a driver question.
Right. So I think what this is coming down to is that there are a lot of ways of talking about this, but economically, if when you pay more for that methanol, say, than commodity methanol, there is the value. I mean, they are making the pledges that this is what they're saying is a value to them. So first of all, the economics should reflect the value, right? So if consumers are demanding recycled content and that's a value to them, and so there should be the value translated in there. But secondly, the impact is very minimal, right? If you were to pay, say, double, right, even double for a gallon of methanol from syngas, waste to syngas, as opposed to commodity methanol, when you finally make a package, right? You look at the weight. A gallon of methanol weighs about 6 pounds, right? So the additional cost that would go into individual packages is minuscule. It's fractions of a penny. So it's something that it's almost imperceptible. But what I say, the answer that I would give is that I would rather that companies, instead of agreeing to pay taxes, which go to basically subsidize the existing system, right? That's why they collect the money and basically keep the recycling system in practice, right? So we're subsidizing a system that doesn't work. I would rather see that money go towards, you know, a truly circular solution. So the money's being spent. The question is it being spent wisely? And I think that paying a little more for the syngas to drive that market, ultimately, I think efficiencies will make it, you know, even more competitive. But right now, the value is there, and the need is there.
Gotcha. Next question is, what are the hazards, environmental impacts, and handling storage risks?
So the hazard, so in terms of this process, I would say very little. There's actually, on these gasifiers, there's no, on a plasma-assisted gasification system, there's no stack, right? There's not a, you know, emission to the atmosphere of all kinds of contaminants like you would see in an incinerator. It's a closed system. We already have the industrial processes that are very natural. We do this in every thermal process out there to clean gas, right? So ultimately, what comes out of this thing is a very clean output. What might get, you know, as in any thermal process like this, you have to clean the gas. So there'll be particulates, there'll be things that are unwanted in there. You know, things like maybe PVC get converted into hydrochloric acid that need to be neutralized. You know, so there's a gas cleaning process where those parts of that will have outputs, right? But those outputs could go right back into the system, where ultimately it gets either converted to syngas or trapped in the you know, in the metal and rock. And those are, you know, I wouldn't say, you know, there's work done here at the University of Florida looking at the leachability, say, of that mineral oxide rock. And sure, everything can dissolve in something, right? So that you can't say it's not leachable. But in normal environmental conditions, these rocks are deemed to be safe, you know, from a leachability standpoint and the environment. So what is the environmental impact? There's not much from that. And then in terms of methanol, it's very clean. I mean, it's it's about the cleanest organic compound there is. Of course, we don't want to drink it. It's toxic to us, but by and large, it's very easy. We ship, you know, that's something we have very good experience with globally.
Great. So the next question is, could carbon dioxide be used to produce syngas at a better rate than carbon monoxide, or would it be energy inefficient?
Basically energy inefficient, because carbon dioxide is kind of like, so it's an interesting thing when you talk about gasification. You know, when we gasify coal, it makes sense. We take a solid and we turn it into gas through gasification. One of the feedstocks we use is natural gas. So it almost doesn't make sense to call it gasification to convert natural gas into syngas. And we don't. So we call that partial oxidation, right? So, but it's the same idea. So the thing is, you know, that's partial oxidation to get to the carbon monoxide. It is complete oxidation to get to carbon dioxide. Carbon dioxide is basically devoid of energy or devoid of anything useful in it at that point. So it is not necessarily a wonderful way to go to use carbon dioxide.
Okay. The next question is, what is the barrier to entry for on-site conversion process?
The barrier to entry is you know, these are not inexpensive, and they require a lot of alignment in terms of what we're doing, right? There's a lot of entrenched players in waste handling, right? In the landfilling business, they make a lot of money. Landfills are wonderful businesses, right? You know, it's a hole in the ground and you put stuff in it. So, you know, Waste Management isn't interested in giving up their market share, and they're not interested in giving up the profits that they make. And you know, who would blame them, right? And sanitary landfilling is very effective for what it does. So they provide a very valuable service. So what this requires is, you know, and this is part of what our initiative is about, is the outreach and education of the key stakeholders, right? So municipalities need to understand that this is a viable option. We already know, we have, you know, on this slide that you see right now, Milliman, a financial firm, has already organized a bunch of major financial companies with pension funds and insurance companies that are looking for sustainability infrastructure investments. There's over $4 trillion looking to invest in this segment. So it's not a financial issue. It's a it's a de-risking policy alignment issue right now. Education.
Do you have information on how much power is needed per volume of output in kilowatt hours if using electric plasma?
I do. I would be reluctant to kind of spew off a number right now, but I would say that let me think. It was like like I said before, in terms of the energy output, you're looking at 5 to 10. It was 5 to 8 times, let's say, of the amount of power it's using if you were making power, right? So, but in terms of producing the syngas, let me hold off on that. I mean, I could get that information. I just don't have it on the top of my head.
Gotcha. And do you foresee this as becoming at some point a profitable business, creating a resource, or more part of our normal municipal services?
It is, well, like anything else. So this is profitable under certain assumptions, right? And that typically involves certain scale. What we found doing the financial modeling is that this is a profitable thing at well, first of all, so what are the revenue streams, right? So a facility goes in, you would expect to collect some revenue from taking the waste. We call that tipping fees, right? So we would collect the tipping fees, and then there's revenues from the outputs, which would be the methanol, the rock and the metals. But by and large, the methanol would be the primary thing. So at a certain scale, which we're looking at something on the order of 500 tons per day of municipal solid waste, a methanol value of somewhere on the order of $1.50 a gallon, and tipping fees on the order of $30 to $50 per ton. At that scale and that kind of equation generally comes out to better than break even, right? We've been doing the financial modeling on this. But ideally, I think we could do a lot more than 500 tons per day, and it really comes down to what industry is willing to bear in terms of the cost of the methanol.
Great. Next question, is there a demonstration that this technology works?
Yes, and in fact, it's I mean, there are a number of, gasification is very old. In fact, your own community probably had gasification before we had light bulbs, right? So we were gasifying biomass and lighting the streets with it. So gasification is not new. The plasma-assisted gasification has gone through some generations of iterating the technology, but it's just it stumbled at one point, I should say, because some folks got very excited about it when they purchased. This is Westinghouse. Purchased the NASA technology that they had developed in plasma torches, and that was developed for the Apollo missions for testing reentry vehicles, and it demonstrated fine at a small scale. But when they scaled it up, plasma torches, like flame, like a candle, has a very hot center, and it cools off very quickly when you move away from the center. So they had a heat transfer problem. That's all been solved with this kind of like lava making machine and here they use stuff from the metals industry. So electric arc furnaces, and these are old. So electric arc furnaces, induction furnaces, things like that. And maintaining a cauldron essentially of molten material improves the heat transfer and basically solve that problem. So right now we're kind of at a iteration of technology that is very effective. And yes, there are demonstrations that work.
Great, and it looks like we've got time for maybe just one other quick question, and that is syngas compressible into a liquid?
Well, sure, but under extreme conditions, right? Because it's high hydrogen content, it is not practical to compress it into liquid.
Great. Well, we have a few more questions. Sorry we didn't get to everybody's questions, but Dr. Welt, as information, and definitely encourage this conversation, because clearly we need something that is innovative to handle this wicked problem of plastics getting into the environment. And Dr. Welt, thank you so much for your time. Folks, thank you all for joining in. If you've got ideas for other Ag Science Cafes in the future, please send them to Vicki McIntosh. And everyone have a wonderful day. Again, Dr. Welt, thank you.
Pleasure.